So the floor is yours.
Okay, so thank you so much for the introduction and give me an opportunity to give a talk at the seminar. So today I will talk about my recent work with Zhao, Hiệp, and Thuy about Newton polytope of good symmetric polynomial, and you can find the preprint on archive. So the outline of my talk will contain 5 parts. The first part I will explain about what is a Newton polytope, and next I will talk about the symmetric polynomial, and next I will explain what is a good symmetric polynomial, and I will explain about the motivation why we care about the Newton polytope of good symmetric polynomial. And in the last part, I will talk about some future work. So first, about Newton polytope. So we consider k point v1 to vk in a real space. And if I take the convex hue of k point, I get a polytope in a real space. And I denote the convex polytope by the convex hue by p. And we say that P is a lattice polytope if all vertices are integer point. And if P is a lattice polytope, we say that P has integer decomposition property. So I denote it by RDP if for any positive integer t and any point lattice point in TP. So they added T point in P intersect ZM. So there are T lattice point of P, say V1 to Vt, so that we can rewrite P as a sum of V1 to Vt. So for example, you see in the picture here, I consider 12 points. So the first 6 points are permutation of 310. So they are the vertices of the blue hexagon, and the next 3 points are permutation of 220. So you see that they are the middle of the sum x of the hexagon, and the next 3 points are permutation of 211, and they are the inner point of the blue hexagon. And now if I take the convex hue of 12 points here, I get a polytope, and in this case that is the blue hexagon P. And we can say that P in this case has IDP. For example, I consider 3 times P, and I pick up 1.921. We can see that we can rewrite 921 as the sum of 3 lattice points. Here I pick up 310 and 310 and 301. And now next F be a function of m variable x1 to m with a complex coefficient. So I can rewrite F as the sum of C alpha x power alpha, where alpha are non-negative point in ZM. And I define the subpart of F to be the set of all exponential alpha, such that the coefficient C alpha are different from 0. And then the little polytope of F is defined by the convex hues of the subpart of F. We say that F has a saturated Newton polytope. So I write S and P if the set of all lattice point of Newton F is exactly the subpart of F. So for example, I consider F in 1,3 variable x1 to x3. Here is given by x power 310 with x power other permutation of 310 plus x power 220 and other permutation of 220 and plus 2 times of x 211 with other permutation of 211. And you can see that in this case, the support of F are 12 points. So you see they are 12 points in the picture here. And we see that they are the lattice point of Newton F. And then we can conclude that F has S and P. Now I will talk about the symmetric polynomial. So we say that polynomial F of m variable x1 to m is symmetric if when I apply any permutation sigma of m element on the variable, I mean on the index of the variable x1 to m, then the function f of x1 to m after the action of sigma does not change. And there are some very special class of symmetric polynomial. They call sure polynomial, and they are defined by partition lambda. So a partition lambda is a set of weakly decreasing integer, non-negative integer. Here, lambda equal lambda 1 to lambda m. And for each partition lambda, we can associate to it a Young diagram. So, namely, a Young diagram of associate to a partition is a set of boxes, such that in the first row we have a lambda 1 box, and in the second row we have a lambda 2 box, and so on. In the last row we have a lambda m box. And the size of a partition lambda is denoted by absolute of lambda is given by the sum of lambda 1 to lambda m. And now for each partition lambda, we can construct the set of semi-standard Young tableau of shape lambda. So a semi-standard Young tableau of shape lambda is a fusing of the Young diagram of lambda by number from 1 to m, such that the entry in each rows are weakly increasing, and the entry in each column are strictly increasing. And for each semi-standard Young tableau T, we can associate to it a monomial T. So it is given by x1 power the number of entry 1 in T, and time x2 power the number of entry 2 in T, and so on. Time xm power the number of entry m in T. For example, when I take lambda is 310, so first I can associate lambda to a Young diagram. So you see that in the first row I draw 3 boxes because lambda 1 equal 3, and in the second row I put 1 box because lambda 2 equal 1, and in the third row I put nothing because lambda 3 equal 0. And now I can construct a semi-standard Young tableau of shape 310 with entry from 1 to 3. So here I can put the entry and the number 1 to 3 in the first row and the number 2 in the second row of the Young diagram. So you see that the entry in the first row are weakly increasing, and the second row also. And when you look at the column, you see that the entry in each column are strictly increasing. Here's 1 is less than 2. And now we can associate to T monomial xt. So it's given by x1 power 1, x2 power 2, x3 power 1. Because here you see that the number of entry 1 in T equal 1. So I put x1 power 1. And now the number of entry 2 in T2. So I put the power of x2 equal 2. And the number of MT3 in T equal 1. So that's why I put x1 power, x3 power 1. And now suppose that we can find the set of own semi-standard joint tableau of shape lambda, and we can find the set of own monomer xt here. And when we sum up them together, we get the Schur function associated to partition lambda. And here I have x lambda of x1 to x3. Here exactly is the function f above. So you see it given by this one. So that equal x power 310 plus something, and it's similar for 220 and 2 times 211. So there are when of fact that's the set of own Schur function, your z basic of a ring of symmetric function. So it means that given any symmetric function, we can decompose. I mean, we can rewrite it as a linear combination of Schur function with a coefficient in z. Now I will talk about good symmetric function. So before I need to define certain order on a partition. So suppose that alpha and beta are partition of utmost m paths. So we say that beta is bigger than alpha if beta I is not less than alpha I for any I from 1 to m. And we say that beta is, beta dominates alpha if they have the same sign. So I recall the sign here is the sum of own paths. So the sign beta equal beta 1 plus beta m and so on. And it also satisfies the condition that the sum of beta I from 1 to g are not, is not less than the sum of alpha I for I from 1 to g for any g. So for example, I have a two partition alpha here equal 3, 1, 0, and beta equal 3, 3, 3. So by comparing the paths alpha I and beta I, you see that 3, 3, 3 is bigger than 3, 1, 0. And the next two partition 3, 2, 0 and 3, 1, 1. You see that they have the same sign. So the sign in this case equal 5 because 3 plus 2 equal 5 and equal 3 plus 1 plus 1. And now when we compute the sum beta I for I from 1 to j and j from 1 to 3, you see that's 3, 2, 0 dominates 3, 1, 1. And as you know before, that's for a symmetric polymer of m variable f, big F from variable x1 to xm, we can rewrite it as the sum of Schur function because the set of Schur function is z basic of ring of symmetric polymer. And now when we sum, when we collect the Schur function of the same sign to brackets, we have this form, the nice expression here. And I suppose that x Schur function in x bracket have the same sign. And we say that f is a good symmetric function if it satisfies two conditions A and B here. So the first condition A states that the support of x bracket is equals the union of the support of Schur element inside the bracket. And the condition B says that in x bracket there is an unique dominant maximum partition, and the set of own dominant maximum partition have a form like first we fix two partition alpha and beta, And then to construct the partition lambda 0 to lambda L in the middle, we follow the rule like this. Suppose that we already construct lambda I minus 1. So to construct lambda I, we just need to put a box in the northmost or in the northmost rows of lambda I minus 1, such that the result lambda I is still a Young diagram or partition, and it is bounded by two partitions alpha and beta. So for example, here if I take f, big F equal S of 3, well, I mean that is a linear combination of sure function here. I don't want to use all of them, but you see that in the expression, I collect the sure function into the bracket because they have the same sign. For example, for the first bracket, the sign equal 4. For the second bracket, the sign equal 5. And the third bracket, the sign equals 6, and so on. And you see that the function f in this case satisfies the first condition A. Here, the support of x bracket equals the union of the support of x sure element. It can be easy need to see because the sign of x sure element in x bracket are the same. And the condition B in this case. So first, I have to fix two partitions, alpha and beta. So in this case, I have, in the condition B, first I have to compute the dominant maximum in partition in each bracket. So you see that the maximum partition in the first bracket equal 3, 1, 0, and the maximum in the second bracket equal 3, 2, 0, and the next one equal 3, 3, 0, and next 3, 3, 1, and so on. And now when we look at the set of all dominant maximum partition, here you see that so you see that they are satisfy the condition B. So the first we have to fix partition 3, 1, 0. So the first one, and the next one is 3, 3, 3. And now we can construct the set of all partition between alpha and beta, so that they satisfy the condition B here. So lambda I is obtained by lambda I minus 1 by adding a box in the northmost row of lambda I minus 1, so that the result is still a Young diagram, and it is contained in the interval of alpha and beta. So you can see, for example, I have 3, 1, 0, and now if I put one box in the northmost rows of 3 and 0, such that the result is still a Young diagram, and it is less than 3, 3, 3, I get 3, 3, 2, 0. Similarly, to construct 3, 3, 0, I have to start from 3, 3, 2, 0, and try to add one box in the northmost rows of 3, 2, 0, so that we still get a Young diagram between alpha and beta. So I get 3, 3, 0, and so on. And you see the picture here is a Newton polytope of F. So you have a 6 polygon color by the 6 different color. And for example, when I choose 3, 1, 0, so the polytope, Newton polytope of S310 is a blue hexagon, and the Newton polytope of the second bracket here is the red hexagon. So that is the one I color in red here, and so on. And when I take the convex hues of 6 polygon here, I guess I get the Newton polytope of F. And our main theorem said that if F is a good symmetric polynomial, then we can say that F has S and P, and the Newton polytope of F has IDP. And a simple corollary of this theorem states that if we replace the condition A by A prime and B by B prime, here A and B are the condition to define a good symmetric polynomial. So, yeah. So if we replace A by A prime, B by B prime by simpler, I mean, they are simpler condition of A and B. The first one says that the sure polynomial in the same bracket have the same sign, and the condition B prime says that there is partition lambda bar and lambda half, such that S will appear in F even only if it is bounded between lambda bar and lambda half. And when F satisfies a symmetric polynomial with two conditions A prime and B prime, we can conclude that F is a good symmetric polynomial, and it has S and P, and use the little polytope of F at IDP. And the application of our result is it cover a number of periods study polynomial, and to find, I mean, I don't want to write all case we cover here, but you can see on my paper. Now I will explain about why we care about the Newton polytope of good symmetric polynomial. So first, Newton polytope has a connection to mathematical optimization and projective toric variety, and they also the central object to study tropical geometry. But here I want to emphasize the connection to unimodal and non concave for the property of RH polynomial associated to Newton polytope. First, I need to explain what is the unimodal, non concave, and symmetric property of a function. So let F, a variable z, to be a polynomial a0 plus a1 z plus a2z d. Here I suppose that the coefficient are non-negative integer. So we call this F here unimodal polynomial if there is an index g such that ai less than or equal ai plus 1 for all I less than g, and ai greater or equal ai plus 1 for all I greater or equal g. And we say that F is low concave if there is an index, for any index I from 1 to d minus 1, we have an inequality ai squared not less than ai minus 1 times ai plus 1. And we say that F is symmetric with respect to d if for all index I from 1 to d, we have ai equal a d minus I. And there are several connections between low concave property, unimodal property, and symmetric property. Namely, to connect low concave with unimodal, we have a statement like if polynomial is low concave, and we put more constraint on the coefficient, that if all coefficients are non-negative, or stronger if all coefficients are non-negative, but there does not exist triple ijk of index ijk in interval 0 to n. such that AI different from 0, AJ equals 0 and AK different from 0, then we can conclude that F is unimodal. And to connect the symmetric property with unimodal, we have some famous conjecture. So here it is a Hebbe conjecture and also Hebbe conjecture and more general Brandt conjecture. So let me explain about what is the three conjecture here. So first, I suppose that P is a d-dimensional convex lattice polytope. Then for any any non-negative integer t, I define IPT to be the number of lattice point at TP, and IPT here equal to has a function of P, and we can associate this function to the generating function named has series of P. So it given by this formula that equal to the sum of IPT z power T and the sum of all non-negative integer T. And we can revise the has series of P as a quotient of two polynomial. So the enumerator are denoted by R star PZ, and we call this one has R star polynomial of Z P, and the denominator equal 1 minus Z power D plus 1, and there are well fact that the coefficient of the enumerator R star PZ here are all non-negative integer, and we say that P is reflexive if its interior contain 0, and the dual polytope P star is also a lattice polytope, and we say that P is Euler-Stein of index R if R P plus P is reflexive for some lattice point V. And there are some factors P is reflexive even only if its interior contains 0, and the dimension of the X series equal M, and the X star polynomial P is symmetric. So we number the first, the second condition by 2, and the next condition by 3. Then the condition F P is Euler-Stein polytope if only if we have a two condition 2 and 3. So from this we can see that we can decide a polytope Euler-Stein. We can study Euler-Stein property by studying reflexive property of polytope. Now I will explain the Hebbe conjecture and also Hebbe conjecture, and the last one is Brandt conjecture. So the Hebbe conjecture says that the F has R star polynomial of P is symmetric. If this one is symmetric, then it is unimodal, and the conjecture were verified for the K of dimension less than or equal 5 by Hebbe in 1902, and it is it have some counterexample even by Painter Mustafa in 2005 and 2008 for the K of dimension greater or equal than 6. So we have a weaker conjecture of Hebbe conjecture by Osugi and Hebbe in 2006, and it's still now open. So it states that if P and it it has IDP. Then it has has star polymer unimodal. And more general, we have branching conjecture. So it is still a long-standing open problem until now. So it states that A, your finite generated CN0, and if it your standard Gorenstein integral domain, then the RH series can have polymer of A in your model. So we can forget about the branching conjecture because it requires more general thing to define it. What is the it has a series of A, but we only need to focus on the second conjecture. So that is the setting for polytope. So if you look at the statement, you see that the condition of P here are Gorenstein and IDP, and the condition IDP, I mean, it connects to our theorem. So our main theorem already give a certain class of symmetric polymer that has IDP. And so it means that we give a certain class of symmetric polymer. It satisfies the condition of Oshui EV conjecture. And so for the future works, so it also related to the Oshui EV conjecture. So we see that we already know that good symmetric function has IDP, and so the future work is to find the set of all good symmetric polymer. We have Gorenstein Newton polytope. So it means that we are trying to find the set of all good symmetric polymer. We satisfy the condition of Oshui-Hibi conjecture, and by that at least we can try to study the conjecture for wood symmetric polymer. And for this purpose, there are a work by Bayer, Hong and Ornstein, Vega, and other authors in 2091. So they already classify symmetric, a special class of wood symmetric polymer. We have Gorenstein Newton polytope. So they did for sure function and inflated grounded polymer. And the fact that the two classes here are already covered by our theorem, so they are wood symmetric. They are also wood symmetric polymer. So thank you for your attention.
Okay, thank you. Are there any questions?
Can I just ask a quick question?
Yeah.
Oh, sure. So going back to your theorem about like good symmetric functions and the new polytope in IDP, like can you say anything about like, okay, I don't know if a converse makes sense, but if you have a the new polytope IDP, like what can you say about like this decomposition to short polynomials? Like knowing that, assuming that the new polytope is IDP.
Yeah, in fact, our theorem already cover no result, and you also cover new result.
Okay.
I think the new result here you can find on my paper. In the next section, I give the dual glutonic polymer. So either a new result, and it is also covered by our theorem. And from our theorem, we can conclude the dual polynomial also has SNP and the little polytope has IDP.
Okay. I see. Maybe it's just participating more than enough. Okay. Thank you.
Is it your question?
Okay. Well, I guess my question is just what can you say about the decomposition to into short polynomials if you assume that your new polytope has IDP, which is going in the other direction? But maybe that's a little bit different from what you're thinking about.
I'm not sure that I can understand the question.
So I guess my question is going the other direction, right? So your theorem says if you assume your polynomial is a good symmetric polynomial, then you know f has IDP and the new polytope has IDP.
Yeah.
But my question is, what if you assume already that your new polytope has IDP? Then what can you say about f given that? Like, for example, like how you would decompose it into short polynomials?
No. It's not a problem. Because when we know a function is symmetric by the theorem here, we can
we know
always.
Yeah, I know we have a decomposition. My question is like, what does it do? Can you say something about what it looks like, assuming that it's IDP? The new polytope is IDP.
Can you speak slowly?
Sorry, I mean, assuming that the new polytope has IDP, my question is, can you say something about like how exactly, like some further information about how it decomposes into these short polynomials? Like some more specific information.
It's not like you have a symmetric function such that the little polytope has IDP, right?
Okay. Yeah, assuming it has IDP, yeah.
And it's not really. They are independent.
Okay.
We don't need to know about the IDP or SNP to know the short decomposition of a symmetric polynomial.
Okay.
But our theorem does give like we have a symmetric polynomial and we decompose them into the sum of short function. And now we form short element of the same size to brackets like this. And then we can find the maximum the domain maximum partition in each bracket. And now what we need to do now is just to look at if the set of partition here they form they have this form. So in page 7 here. And if we see that if they satisfy the condition B, then we can conclude that our symmetric function SNP and each little polytope has IDP. So that is some kind of simple rule to define if a certain symmetric polynomial has SNP and each little polytope has IDP. It's very simple. When you look at the example here, you just usually to look at the short decomposition, and you form short element in the same size to bracket. And next you find the maximum partition, and then try to formulate them to the form in the condition B. And if we satisfy the condition B, so we can conclude that it is IDP. The little polytope has IDP. It is trivial, and the rule to determine if a symmetric polynomial here is SNP and as little polytope and IDP. It covers a lot of rules, and it tell you what is the main point for the condition IDP and SNP. If you look at the case of inflatus symmetric polynomial, you will see that they have a lot of conditions, and some complex argument before they can decide. They can tell you about the IDP and SNP of the inflated polynomial. the rule behind the rule. The main reason behind such kind of argument not clear, and our theorem here just collect the main condition that implies the IDP and NP, and its state will be A and B, and it's simpler. If you read the proof of our theorem, we already give some argument more general, and it not depend on the choice in the proof for NP and IDP of inflatable platonic polynomial.
Thanks.
Okay. Are there any other questions? Well, if not, I stop the recording.